Yeah, I'm a PhD student from Bielefeld University, and our talk is about benchmarking neuromorphic hardware. So we see more and more hardware systems appearing in research and industry, and the question arising is whether or how do we compare the performance and the efficiency of these quite diverse systems? That's the main question guiding our research here. So our neuromorphic benchmark approach is a black box approach. So we take the user's perspective and have a very high level description of our spiking neural network. And that is mapped via an abstraction layer to these various different target systems. By this approach, we can provide direct cross-platform metrics and have, as I said, the backend independent implementation. However, due to the large variety of these systems and the different hardware sizes, different network sizes supported, and different neural models, we have to open the black box a bit, so we allow platform-dependent configuration of these benchmarks. And the framework we are doing all this in is called SnapSuite, the Spikey Neural Architecture Benchmark Suite. So most of our target platforms are already known to the audience. That's why I will not go into details, but I like to highlight one thing, that we are comparing very modern CPU and GPU implementations to the rather old technology used in the Spinnaker, Spikey, and Brainscale systems. So you have to keep in mind that by just porting these systems to more modern technology, you probably gain an order of magnitude in efficiency, just for interpreting the results I'm showing. Since the field of neuromorphic computing has not yet have the spiking neural algorithm that solves everything, we have different levels of benchmarks to be still quite representative of the field. And this starts with very low-level characterization benchmarks, measuring low-level properties of a system, and ends up with full applications with performance metrics that are very specific to a certain task. And to bridge that gap, we have in between these application-inspired subtasks or computational kernels whose metrics are somehow applicable to a more broader range of applications. And to fill these ideas with a bit of, to fill these ideas, I will present benchmarks of all these categories now. We start with a low-level characterization. On the left-hand side, you see a benchmark measuring the readout bandwidth of a system. That means we have a population of neurons that is constantly spiking without any input, and just measure how many spikes can we really read out at the end. And you see that on the Spinnaker system, you actually have no problem here. The average output rate per neuron is basically limited by the time step of the integrator that is in use. On the Spikey system, you see that you have very high rates for a very small portion of the system. However, when going to larger networks, then you see that this average output rate decreases. This is basically due to the high acceleration factor used in these analog systems. On the right side, you see the input bandwidth benchmark. We cannot directly measure the input bandwidth, so we measure the response of a population of neurons to, in this case, a one-to-one insertion of spikes. So spikes are inserted at the same time to all neurons in a population. And you see that on Spinnaker, the response goes down rather quickly too, because this has two reasons. There might be issues in the off-chip network, so spikes are lost on the way to the target neuron. But the more relevant case here is that the individual cores are overloaded with the amount of spikes reaching the core at the same time. So these bottlenecks you have to keep in mind when designing an application for these systems. To go further, one application-inspired subtask is the winner-takes-all network, which is the basis for a broad range of applications. And here you see some raster plots from Winetics all implementation on some target systems. And you don't see that very well here, but on analog systems, you have large neuron-to-neuron variation. And our problem here was that we tried to make both populations more or less be activated with the same probability. This is not always the case on an analog system. So an algorithm that relies on all the populations becoming active with the same probability will probably have a reduced performance on an analog system. And such an application would be solving constraint satisfaction problems. Here we take the Sudoku puzzles as a representative of this class of problems. And as I already indicated, you see that on analog platforms, the accuracy is actually a bit reduced compared to a digital simulation. However, you also see that the energy to solution is orders of magnitude better than in a simulation environment. Going to larger networks, you also see that the accuracy gap between a Spinnaker simulation and a CPU simulation closes a bit, indicating the good performance of the Spinnaker system for larger networks, because the utilization in these networks was not at 100%. So yes. Another application-inspired subtask is related to the conversion of rate-based deep neural networks. So you can look, or this conversion process relies on the resemblance of the activation function of individual spiking neurons to the ReLU activation function. And here you see that this is more or less the case for the Spinnaker Gen simulation. Up to something like 250 hertz. It also depends a bit on the parameters in use. For Spikey, you see saturation appearing at about 150 hertz, and you also see that is indicated by the shaded areas that there's a huge variation with these neurons. So again, we expect from this benchmark that the actual accuracy on the real application is a bit reduced on analog systems. And one very small rate-based deep neural network that is really suited to be put onto Spikey has some limitations like only positive weights and no biases and so on. The conversion loss is quite high in the direct conversion process. However, we can recover some of the accuracy by doing in hardware in the loop retraining. Again, we see that the energy per inference is at an order of magnitude better on an analog platform compared to the most efficient digital platform, which is in this case a GPU implementation on the NVIDIA RTX 2070. Going to larger networks, we took a pre-trained network as well that was openly available on GitHub, and this is not suited to be put onto Spikey anymore. And we see that now the larger Spinnaker system, now with 100% utilization, can reach the accuracy or even overcome the energy per inference of a CPU simulation. So it has a better energy per inference metric. However, still the GPU is the most efficient platform at the moment. And this also doesn't change if you go to time to first spike encoding. So I have 1 minute left, and I will summarize that all these presented work is openly available on GitHub. We presented an initial set of benchmarks that is currently implemented, providing cross-platform metrics and backend independent definitions of neural networks. On the Outlook side, it would be great, of course, to implement more benchmarks and also to support more backends. So in principle, our framework is suited to be extended to both of these. So I'd like to thank everyone from all these respective platforms for their continuous support. And with this, I'd like to end my talk.